electron affinity. This is to create a negative ion, an anion. So it's the energy released when we add an electron to a gas phase atom. So for the anion to be stable, it has to release energy. So this is an exothermic process. And the more stable the anion is, the larger our electron affinity is. So a zero electron affinity means that the electron is not stable and it will fall off. So the general trend for electron affinities. So electron affinity is an exothermic process, is negative. Some authors write it around so it looks positive. We don't worry about the sign as much, but the large electron affinity means a stable anion. So an electron affinity becomes larger as you go from left to right across a period. We're going to exclude the noble gases. Their electron affinities are going to be close to zero. They're not stable. Halogens have the largest electron affinities. So electron affinities increase as you go from left to right to the halogens on the periodic table. The trends up and down the columns, up and down the groups, are not very dramatic. So their main trend is going from left to right across the periodic table. So these are values for electron affinities. They're shown as enthalpy values. So they're negative to show that they're stable. They're exothermic processes. And we see that our halogens here have the most stable electron affinities, the largest electron affinities. We do have some elements that show up as being stable, also gold, acetine. But our main trend is going across the periodic table, left to right. We have a decrease in our, we have increase on electron affinity, decrease in the sign, increase in electron affinity. The elements are becoming more stable going from left to right across a period in the periodic table. The trends in the groups aren't as consistent. So for the halogens, chlorine is the most stable. So period 3 is the most stable. So fluorine is not quite as stable. So we're going to become more stable with period 3, and then they slowly become less stable as they go down the column. For oxygen group 16 here, again, it becomes most stable on period 3. That would be with sulfur, and then there's a slight decrease in stability going down the table from there. Yellow here is the noble metals, group 11. In that group we see that it becomes more stable as you go down the column. Let's see, what else do we have? Group 15, the nitrogen group. We have a slow, gentle increase down the column mostly. But not consistently. It gets a little bit less stable at the bottom by bismuth. And group 14, carbon group, becomes most stable at period 3, and then slowly becomes less stable. So we don't have a consistent trend for group 17, 16, 15. We are the most stable on period 3 with a slow decrease in stability from there. But that trend doesn't follow for group 15, so it's not a consistent group up and down the group. Although the one trend that we see, but not for every group, is that period 3 has the strongest electron affinity. So we do have some trends that we can, exceptions to the trends that we can identify also. So we're going to expect to see small electron affinities when we have a stable electron configuration. So it's going to be harder to put an electron into a stable electron configuration. We'll have a larger electron affinity when we are creating a stable electron configuration. So for noble gases, since they are extremely stable, their electron affinities are small enough to be essentially zero. So for group 2 elements, we have a complete shell. So our next electron will be going into a new level. That means group 3 is going to be smaller electron affinity than group 2. Period 2, excellent. Okay. So we'll look at this in the next couple charts. Then also, when we have the half-filled P sublevel, this we saw in the ionization energy. This is a stable configuration, and it remains stable for electron affinity. So for group 15 elements, when we have the P sublevel half-filled, it's going to be harder to put one more electron in. Also, when we have a filled D sublevel, the next electron will be difficult to add in because it will be the first electron in P. And then for group 7, when we have a half-filled D sublevel, first electron will be the first pairing on the first pairing up of an electron in the D sublevel, so it's not quite as stable there. So for period 2 here, we see that when we have the complete S sublevel, the electron affinity is essentially zero. It's hard to put that first electron into P. So now we have our first electron, second electron. At this point, we're putting our third electron in. So we have a reasonably high electron affinity to put our third electron in to the p sublevel, so that'll give us a half-filled one. But once we have that half-filled sublevel, electron affinity again drops down to essentially 0. It's difficult to put the fourth electron in. But then when we have 5, we have a large electron affinity because it's easy to put the sixth electron in to complete the p sublevel. For period 3, when we have a complete s sublevel, it's difficult to add electrons, so our electron affinity drops down to 0. It doesn't want that first p electron. But we have first, second p electron. Second p electron, we have a large electron affinity. So for silicon, it'll take the electron easily because that will complete the half-filled p sublevel. But once we have the half-filled p sublevel, electron affinity drops because it's hard to put in that first paired electron into the p sublevel. And then when we have the 5 electrons in p, we have a large electron affinity because it'll readily take one more electron to create a completely filled p sublevel. Period 4, we see our d sublevel for the first time. But again, when we have the filled s, we have a lower electron affinity because it's hard to put that first electron onto d. When we have when we have 4 electrons in d, we have a relatively large electron affinity because it will be happy to take the 5th electron. But once we have that 5th electron, the half-filled d sublevel, electron affinity again drops close to 0 because it does not want to do the first pairing on the d sublevel. We go up to 9 electrons on d, and we have a large electron affinity because it will be happy to take the 10th electron. But once we have that 10th electron, electron affinity again drops down close to 0 because it's difficult now to put in the first p electron. When we have 2 p electrons, we have a large electron affinity because it will be happy to take the third. But when we have that third p electron, we have the 1 electron in each sublevel, each orbital of the p sublevel. Then it's hard to put in the fourth one, so we have a lower electron affinity when we have that half-filled p sublevel. And of course, when we have 5 p electrons, we have a large electron affinity because it's very willing to take the 6th electron. Period 5, we're still seeing these trends. So when we have the s sublevel filled, electron affinity is low because it's difficult to start with d. When we have the d sublevel half filled, we have a very low electron affinity, close to 0, because it's hard to put in that first paired d electron. When we have 4 d electrons, it's not the highest one. In here we're starting to see more shifting of electrons between the s and the d level, which shifts things around. We see that over here for palladium, where palladium is taking both s electrons and shift them over to the d. So we have a complete d level, and the electron affinity drops because it's hard to either put electron back into the s sublevel. And over here for cadmium, we have a low electron affinity because we have the s and the d both completely filled, so it's hard to start the first p electron. Then we go to the first, second, third p electron. We have the p level half filled, and it's a slight decrease from having 2 electrons in the p sublevel because it's hard to put that first paired p electron in. And of course 5 p electrons is real high because it's very happy to take on the 6th p p electron.